Okay.
So that's a good
Let's see.
thing. Do I have permission to do it, or?
Settings. Let's see. I think everyone should have ability to share, but I will double check.
Hold on, let me exit and come back in. I think I clicked on the link from Discord, so it's opening it up within Discord on my iPad. So let me.
Okay.
That might be
That
it. Yeah.
that could probably be the reason.
I don't know. I have the permission for sharing my screen.
Sharing,
also.
yeah.
I came here by Discord link, so.
Okay. Yeah, I think it's probably to do with the way he joined. Okay, some more people joining. That's good. We have more people joining. Actually, I was meant to send an email newsletter, but I was like, okay, vast majority of people who are interested in the course are on Discord anyway. So, and some people are on the have already subscribed to the YouTube channel, so they get the notification.
I will try to fill the form again because
No, I have your form.
Okay.
Yeah.
Okay, so I think
you don't need
no.
So we are just we three here.
It might be that, yeah.
Yep, you can. We can all see.
Okay,
I can. Right.
Yeah.
I can see your note, your notebook, your sheet, note sheet.
So, since I'm disappearing, maybe Antonio, you probably could help Brian if anybody asks any question or something that he missed.
Yeah,
if that's okay with you.
Right.
Yeah, stay for as long as you want. You don't definitely not to stay for the whole thing.
As long as you are on the call, or anyone on the call, please feel free to jump because you do have permission to speak to Brian. It's because I need to go. Yeah.
Right. I mean, so if Antonio leaves and you leave, we'll just keep the thing open for an hour.
No, it will stay open until I come back. Yeah, and it's recording as well on YouTube. So yeah.
Cool. Perfect.
Great.
All right, so I leave it to you, Brian. If you want to wait and a few minutes to start, it's entirely up to you guys, or you can just crack on. I'm disappearing. Thank you again for everyone for coming. Thank you, Brian, again for your taking your time to do this. Okay, we catch up next time, guys. I'll see you. Enjoy your session.
Thank you for organizing this. Thank you.
So actually, Antonio, I thought about some of your questions from last week about UNETA and Cayley theorem and all those other fun things. I posted some links in the Discord channel. One is just kind of a loose philosophical interpretation of how to think about UNETA. It's a cool metaphor in terms of particle accelerators and probing things. If you send every possible kind of energy level and particle at something, you understand how it reacts to everything, and so you characterize the object completely. It's kind of neat but loose. And then also there was a really cool post about explaining UNETA element to an analyst.
Great.
Yeah.
I saw, but I will try to pay the time for understanding the post. Later. Right. My apologies because I wanted to look for some information this week, but I had no time. Finally, I'm trying to. But right. Thank you for that.
No worries.
I'm quite interested about UNETA lemma actually to understand it well.
So here's the start of that kind of thing. So the context for this explaining to an applied mathematician is using the UNETA lemma to understand the construction of the real numbers in terms of Dedekind sets or Dedekind cuts. So it starts like this. So, if we remember, so we'll kind of come back to this thing. So we'll start with some post set, but in general, you're right. Before we have some locally small category. Let's see, the locally small category. Locally small just means like all the hom sets are actually sets.
Right.
And then you can either write like this, it's like C with a caret, or this bracket notation, which just means the collection of, it's the category of functors that are contravariant from C to set. So this is the contravariant.
Right.
Two sets. So one kind of thing to note is, if you start with say like a small category, which means that the collection of objects is actually set, then this functor category will actually be big. It kind of increases the size of the category for sure. And all right, so we have that. So the Yuneta embedding was this fully faithful embedding, or fully faithful functor from C into the functor category. I'm getting all the extra details for anyone who ends up watching the video a little bit later on. So we send an object X to this functor we said it was H to the X, which is a set of all morphisms, from some object Y into X. So it's a fully faithful embedding by the Yuneta lemma. So I'll just write it as like a little hook on the end of the arrow there, for kind of like an injection. So in this example of post sets, I think I gave in maybe lecture 1 or lecture 2, you can regard any post set as a category.
Right. It was in the first video.
So this is, it's a kind of category where the set of objects is just the set of elements of X, and so objects of this is just the set X itself, and then for any two elements, say X and Y and X. And this set of homomorphisms is either a singleton set or it's empty, right? So it's equal to, so there's a unique morphism from X to Y if X is less than or equal to Y, and it's empty otherwise. So all this does is just kind of, you've got your collection of elements, and this unique arrow just keeps track of the, the ordering on the objects. So what Yuneta is telling us is, Yuneta interpretation, that an object, fundamentally, X in the category C is the same thing as the functor H to the X in the functor category. Right, we should kind of regard them as the same object, and using the embedding, we know that any homomorphism from Y into X corresponds exactly to some natural transformation from H to the Y to H to the X. So in terms of post sets, what we, maybe I should use a different notation for object, because that's going to be confusing. Maybe like A. What Yuneta is saying here is that any element of this post set is uniquely determined or equivalent to this sort of collection of all elements that are less than or equal to X, or maybe greater than or equal to X, depending on how you want to order things. So this is like X less than or equal to little x. Because what is this? So this is sort of precisely all the elements such that you have a non-zero morphism between the two. So from this kind of collection of objects that's kind of downward pointing, you uniquely recover the element X. You can also do it the other way around if you have a different order. So,
Okay. So you can get or define the in a partial order set. You can define each
Yeah.
element by all these elements below it. This
yeah.
approximating it by its from below somehow. It's like right.
So if I have, a bunch of objects like this, then, and this, the top one is X, this is just saying that I think about X as sort of, in some sense, like the maximum of this thing.
Right. It reminds me to cofinalities actually.
Yeah.
And that's something important in set theory.
So the cool thing is, so we can make this more precise, and you can actually look at, if you look at the UNet embedding on these categories. All right, I'm just gonna write X to, if the order is implied. So I don't have to keep writing it each time. I'm thinking about each element like this, which is really just this functor. So this is the idea. But this is kind of in bijection with this set. There's some extra kind of terminology that we haven't covered yet, but in that second link I posted about explaining UNETA, using UNETA to explain the real numbers, you want to think about this association as in analogy with that of Dedekind cuts for rational numbers. Is analogous. The Dedekind cuts are one of the axiomatic ways of constructing the real numbers from the rational numbers, where you use the fact that the rationals are a poset, and so a Dedekind cut is sort of a partition of Q into two sets A and B. At least one of these is non-empty. A is closed downwards, and A has no maximal element. It's like the canonical example from, I think, like the first or second page of Rudin's intro analysis book is thinking about the square root of 2 as the same thing as a set of rationals such that y squared is less than 2. This is an example of a cut.
Okay.
Oops.
A question also about the plan. Do you plan to explain or show Kang extensions in the future?
I can. So I think the nature of this thing was that it's pretty abbreviated, so we can really only touch on a bunch of the core concepts. So by, I think, maybe lecture 5 or 6, we should maybe be able to at least touch on them, because next time we're talking about limits and co-limits, and then adjoints after that. And so at that point, you can go full on, there's this awesome, chapter in McLean's book, where it's just like all concepts are conic extensions.
Exactly. Right. Actually, the beginning of this chapter is also about how to define the reals.
Okay.
Right.
Anyway, so I'll get back to this example a little bit later on in more detail, maybe by the end of the course. But you can essentially recover the process of Dedekind cuts or the reals as so if I let 2 be the category with 2 elements, say 0 and 1, and the unique morphism between them, which I'll call like maybe P, and I look at the functor category from Q into this thing. So this is essentially, just picking out whether or not a given element is less than a given element. Sorry, less than something else. So if I have this embedding right here, UNETA, these are precisely my brain just kind of shut off for a second there. So element of this thing is a functor variant to 2, so it sends some rational number to either 0 or 1, and we send the relation x less than or equal to y to this unique morphism from 0 to 1. Then what this post does is kind of neat, is you can recover. So like the image of Q inside this functor category is isomorphic to its image by UNETA, but we cover the reals inside this functor category as the collection of all non-constant functors that sort of preserve small limits, or small colimits.
Okay.
So in this post-it category over Q, small colimits correspond to increasing sequences of rational numbers. And so if they're non-constant, you're just looking at non-constant increasing sequences of rational numbers.
Nice.
So that was kind of neat. That are non-constant. So preserving small colimits is the same thing. It has a name called being co-continuous, which means that if I have some embedding of small category inside, say some category C, and I look at the colimit of this thing, which we'll talk about maybe next class. So this is another object of C, and being co-continuous just means that f of the limit is the limit of the f applied to the alpha i's. Like this. Yeah. So once we kind of cover some more of these terminology in the future, we can maybe do that example a little more detail. I also want to talk about the using UNETA to recover Cayley's theorem from group theory. That was something you mentioned last time, I think. Was that you or somebody else?
It was me, I believe.
So UNETA lemma implies the Cayley theorem for groups. So let G be some group. So there's a way to consider any group as a category, where the category will have only one element, and then all the elements of G correspond to morphisms in this category. So
monoids. So
yeah, so it's like a monoid, but now every morphism is also an isomorphism. So you can think about a group, or maybe a groupoid, as a category with one element where every morphism is an isomorphism.
Okay.
So here's associated category. So it'll have one object, which we'll just call star, and the set of morphisms from star to itself is in bijection with the elements of the group G. So you can think about this thing as very analogous to any element of a group determines a automorphism of that group.
Right.
So you do
It's like natural numbers. Pick one
Yeah.
natural number, or natural, not sorry, not natural, but let's say uh, integers. Pick
Yeah.
one integers, and you can construct the automorphism summing this integer to the wall.
Exactly. You send the element little g to the automorphism multiplied by little g,
For
multiply on
example,
the left, say. Yeah.
right.
And then you notice that the inverse of this isomorphism is exactly the image of the inverse of g.
Right.
So once we do that, okay. So what does UNETA say about this category? Apply to the category CG. So it says that we have a fully faithful embedding of this category into the functor category sets. H by UNETA. But in this case, what does like a set valued functor on G look like? So contravariant doesn't really matter because it's, well, it's okay. It doesn't really matter. A set valued functor here is really just the same thing as specifying one set. Because there's only one object of G of the category CG. So you only have to, make one assignment. F from CG up to set. We have one object over here, star, and it gets mapped to some set, whatever you want to call it. Let's say S. So this is equivalent to just specifying one set. And what does the data on the morphisms do? So we know that F sends. So I'm going to think about the morphisms star to star. I'm just going to write them as the phi sub g because it helps us kind of remember how to think about them. So it sends the morphism phi sub g to some morphism set from f of star to f of star, which is just a set valued function from S to S. This is set function. But because every morphism in CG is an isomorphism, this actually is a function from G into a set of bijections from S to S. So this is because each phi G is an isomorphism, and you use functoriality.
Okay, and all bijections will be described by all permutation. The permutations possible.
So a bijection from S to S is exactly an element of the symmetric group on
Right.
set.
Okay.
Mhm.
Okay.
Yeah, and so what this basically says is that Cayley's theorem just says that any group is a subgroup of some permutation group. In particular, usually take the underlying set of G itself. So this is a embedding as subgroups.
Okay. So the key point is to describe the group as as morphisms, right? Not looking at the group as an object, but as
Right.
the right, as the set of morphisms.
Mm-hmm.
Right. Great.
You use the morphisms then functoriality to kind of preserve that structure.
Okay. It's a little bit different that I was thinking, or I was trying to think about before. I was
Yeah,
cons-
it's. Go
right.
ahead. Sorry.
No. I was trying to look at the group as objects and right
Mm-hmm.
and think about how to identify objects, not thinking about morphisms. So I was in the wrong way. Nah, okay.
So
That's
that's kind of the trick, because you really want to use this functoriality that says if I have, two elements of the group G and H, if I compose those morphisms, I get the composition on the other side in the category of sets.
right. The
And over here, this is the same thing as G times H.
right. The important thing in a category are morphisms, actually. We say that more than objects. So it's a good thing to try to think about morphisms always.
Or rather, I'd say that they are of equal importance now, whereas maybe in a traditional set theory perspective, the morphisms are, extra things that you use to study objects rather than being as equal important.
Right. Okay. Right.
So that's kind of a fun application of this thing. So UNETA is everywhere.
Right. So it is a nice theorem in group theory. The Kelly theorem is a nice one. We can see here the connection clearly.
Yeah. There's even like the kind of immediate analogy in just classical analysis, where you can send any smooth function to the distribution, which is just given by integrate against this function. So if I take some smooth, compactly supported function with some manifold M, or maybe Rn, say, I could integrate against F. And so you can sort of regard this distribution as the same data as F. And in particular, there's a result that if these two associated distributions are equal, then you actually know that F and G are equal. Maybe I'll write like this. Which is exactly the same thing as UNETA, right? That if these are equal, then these are equal. So it's a really pervasive idea. By understanding a category by embedding in some bigger category that lets you sort of model generalized objects of C. So if you don't have any other questions, I can talk about some of the sort of, I hesitate to call them exercise, but like random things I ask people to do during the lecture. But do you have any other questions?
I had a question from the lecture for today about that you were talking about the kernel as the final object, right? And then we see that we can find a unique morphism to any other normal subgroup to the kernel. But when we have morphisms between other subgroups, these morphisms could be not unique if we can include. I am a little bit confused because We are showing unique morphisms by dash arrows, right?
Yeah,
Uh,
yeah.
And okay, so we have a unique morphism
Mhm.
from any other subgroup
Right.
into kernel, but not between the morphism between two subgroups. In the
Mhm.
case that we can construct it, uh, are not sure. That doesn't have to be unique. I am confused about that.
So I'm trying to understand your question. So you can rephrase this uniqueness problem. Like in this example, it's kind of nice. Is if I have any other, say, normal subgroup, or it doesn't have to be normal, any other subgroup, um, say n of G, such that the map 5 restricts, if I restrict 5 to n, I get always equal to 0, then you must have n itself as a subgroup of the kernel. And this is just because of how you define the kernel, classically. It's exactly all elements of G that are killed off by phi. So in particular, n is in a subset of G. So every element of n is also killed off by phi. So it must be in the kernel.
Right. But
So we'd go ahead.
But the question is that this diagram, let's say that we have of course, N is a subgroup, and we could have another subgroup, M. Actually, it is in general, right?
Mhm.
And
Sure.
right. So if we have an arrow from M to N, right?
Mhm.
M in this case, M having the same rules than N. So we have
Mhm.
the same diagram for M, right?
Right.
So if we
So
have the arrow from M to N, this
mhm.
arrow is unique. That's the question. Has to be unique.
No, it does not. So what happens now is that just because you have a unique morphism to the kernel as the terminal object
Right.
doesn't mean that the other objects that can map into this are like partially ordered in any way. So for example, in analogy with the category of sets in the terminal object, which is a singleton set. So this is terminal in set, meaning that every set X has a unique morphism to the singleton set. It does not mean that any two sets have a morphism between them that's unique, right? Just because these like X and Y have a unique map that sends everything to just the one element doesn't mean I can like a priori relate X and Y by some morphism.
Okay.
So the collection of so I guess just because M and N are killed off by phi doesn't mean that they're necessarily partially ordered or related by some map, unless you know more about the group in particular. I'm trying to think, like if I have some kind of maybe I have something like this and I have like 3 copies of it, and the map like kills off 2 of those copies. It projects into the third vector, or the first vector, let's say. So it sounds N M K to N. Group homomorphism, and the subgroups 0, 2Z, 0, and this are both in the kernel. But there isn't really like an inclusion or a morphism between the two subgroups.
Okay.
Mhm.
Okay.
Does that help or make sense? So the only uniqueness thing that you get is just to the important object that's universally defined.
Okay.
So one other thing so to think about all these things as subgroups, you do want to always kind of ensure that this is an injective group homomorphism. And one thing I was sweeping under the rug was how do you characterize the image of a group homomorphism as a universal property? So one thing you can maybe start at is the first isomorphism theorem for groups. And so what does this say? It's like, given any group homomorphism phi, that the kernel is a normal subgroup. And moreover, that G mod the kernel is isomorphic to the image. So one perspective we could do, if we're kind of sneaky, is apply. So instead of bring it apart. In the lecture, I talked about the kernel and the co-kernel in terms of universal properties. And if we're clever, we can regard the image in this manner too. So if I have the natural quotient sending G to G mod the kernel, we'll call that Q, then the co-kernel of this thing, sorry, that's not the right one. That's one morphism we have, but I could look at the actual inclusion of the kernel into G, the co-kernel of this morphism. This is exactly G mod the kernel, which is the image. So if you can understand how to write the co-kernel in terms of a universal property, then you can characterize the image of a morphism universally as well. You can actually, it's kind of a silly thing, but one way to phrase the first isomorphism theorem is that the co-kernel of the kernel is like the kernel of the co-kernel. Where you think, you replace kernel and co-kernel as not just the subgroup, but the morphism. So here I think about the data of this inclusion is the kernel, and I think about the data of this as the co-kernel.
Right. The same structure.
Mm-hmm. You can also phrase this thing as, the image is the smallest subgroup of G, so subgroup of G, such that there's a surjection from G. This is a surjection followed by an injection. It's the small subgroup of H, such that I can factorize phi as a surjection followed by an injection.
Okay.
So this actually ends up being a very useful, description maybe in other categories or in general. Thinking about an image of a morphism, or like being able to take any morphism and factorize it as a surjection followed by an injection. Kind of a very powerful tool. Another universal property I wanted to talk about was quotient objects. So like quotient groups, quotient vector spaces, quotient spaces, in different categories. So in the category of groups, vector spaces, and topological spaces. It's maybe easiest to spot the universal property for topological spaces, because it's almost kind of defined that way. So if I have any topological space X, and I have some kind of equivalence relation on it, I can form the quotient space x mod tilde, where you just send some element of x to the equivalence class containing x. And x mod tilde has the topology determined by if I have an open subset, u of this quotient is, or sorry, subset is open if and only if its preimage is open. This is topology. So the universal property of the quotient in this case is that if I have any continuous function, say from x to z, we call this, I just use like little g's all over the place. So maybe I'll call this f. So suppose this is continuous, and if I have any two elements, little x and y, so little x1, x2, and are related by the equivalence relation, then, so if that implies that their images are equal, then the universal property says that there exists a unique morphism from the quotient. So diagrammatically, it looks like this. So you get to kind of complete this diagram with a morphism here. And it's defined in sort of the only meaningful way, which is why we like universal things. I send an equivalence class to any representative of it. If f is constant on the equivalence classes of x, then it doesn't matter which representative you choose. So the philosophy is, if f is constant on the equivalence classes of the relation tilde, then it descends to the quotient. So this is sort of how you think about the quotient universally. You can also do the same thing with any kind of quotient map. You can replace, if Q is a quotient map, you get the same kind of thing. But now you want to say F is constant on the fibers of Q.
I believe that I don't understand still what does it mean that descends the quotient.
So you want to get if you quotient x by this relation,
right?
And maybe you want to extend the map F. Like you want to somehow find a way to complete this diagram. Get back here. So we want to somehow complete this diagram.
Right. Okay.
So one candidate for doing this is to say, well, I want to define F on equivalence classes of the relation. But this is only well defined if F can't tell the difference between elements of an equivalence class. So if x1, x2 are related by this, implies this, then it can't tell the difference between elements of an equivalence class. So we just say, we use the phrasing that it sort of descends to the quotient, or it kind of factors through this map Q somehow.
Okay.
So for maybe groups, if it's better,
So
we can do.
it is a way to define F. through this another. It is
Mhm.
F already defined, or it's so it is not. It is
So
sorry.
think about this example where I have R to maybe the non-negative reals, or maybe let's just do R to R, and the map F sends X to X squared. Then suppose I define the relationship on R that X is the same thing as minus X. So identify any number and its negative. So the resulting quotient here is precisely the non-negative reals. You kind of just like glue the line together, fold in the middle. So squaring a number can't tell the difference if the number is negative or positive, right? Because you kind of get rid of the minus one. So in this case, we can sort of factor this map through the quotient. So the factoring through the quotient really just means that the map F contains some redundant data.
Okay.
So all you do, you're not really like, defining it a new way. You're just saying, throw out the things that F can't like distinguish between.
Okay.
In group theory, you have the same kind of thing that if I have, say, some normal subgroup of G and I look at the quotient, so this is the collection of, say, left cosets of G and N. Then if I have some group homomorphism phi, and phi, if, let's say, GH inverse phenomenon of N, so this is the same thing as they define the same left coset. If this implies 5G equals 5H, then you can define a map 5 tilde on the quotient by sending the left coset Gn to 5G. So it's the exact same diagram. You can just say this. You can do the same thing with vector spaces, where if I have some subspace V of W, or some field K, whatever, the quotient vector space looks like the collection of cosets of this form. This is a vector space, and if I have a linear map, just say some vector space U, and it can't tell the difference on cosets. So if X minus Y is in W, implies 5X equals phi of Y, or sorry, psi, I keep fucking that up. Then you get a unique extension of this thing to the quotient. So it's different contexts, but they're all the exact same universal property. And that's kind of the tagline of category theory. It's context sometimes doesn't matter as much as the semantics.
Right. The construction is the same.
So if you like the kind of algebraic side of things, a really important collection of categories, or like a context for doing math, is something called abelian categories. So this is like, for example, something that I almost exclusively work with. Abelian categories. So these are basically a sufficiently robust, nice category in which you can do homological algebra, whatever, if that makes sense to you. You have an initial and terminal object. So you have a zero object, like the trivial group, the trivial vector space, and so on, which is both initial and terminal. All of the Hom sets are actually abelian groups. You can always add any two homomorphisms together. You have an analog of the first isomorphism theorem, which you have to kind of map out in terms of universal properties, and a couple other nice things. So this is sort of sufficiently nice context for abstract algebra. So examples of these are like the category of abelian groups, not the category of groups. If you have the problem with having the whole category of groups is that you have this thing where you can't always take the quotient by any subgroup, right? Not every subgroup is normal. But if you have an abelian group, every subgroup is normal. That's like one of these nice things that makes that work. The category of vector spaces over a field, category of modules over some commutative ring, or the category of sheaves of vector spaces on some topological space, or functor categories. So it's really, hammers in that the context kind of matters less than the rules that you use to work with them. So this is sort of the starting point for, say, modern algebraic geometry, and something called derived categories, which are sort of like my main set of tools that I use to study topological problems using algebra.
Right. It is. It seems that you like a lot of this stuff. Maybe related to your to teach your doctorate.
Yeah. It's sort of it's a way of translating kind of difficult topological problems into concrete abstract algebra problems. I like that. You can also do similar kind of things with like set theory and logic. You can look at categories called like a topos or an elementary topos or a Grothendieck topos. These are like sufficiently nice contexts in which you can describe foundations of math or describe something like set theory.
Right. These are contexts like you can do math like you do somehow in set theory. Looking like set theory.
Yeah, and the cool thing, oops, one sec. Stop sharing. The cool thing is that these are essentially equivalent languages from the right perspective. You can, like topos theory comes up all the time in geometry too, and not just logic. So the fact that these are actually the same set of tools is a really cool, I don't know, connection, I guess. Yeah.
Right. These kind of connections lead us to ask ourselves at the end of the day, well, okay, what is geometry? Right.
Yeah. What is a space?
Right. It's it's like mind blowing. I like that.
Yeah, I came up with this, or I came across a really cool application of this idea that's very straightforward. In the past few years with my work, where you can take any topological space and turn it into a poset, right? Like you look at the collection of open subsets of the space, and you can look at that as a category in the usual sense. And So one of these things from Topos theory is the idea of starting with like any category and kind of endowing it with a certain topology or collection of distinguished elements and collections of morphisms that you think about as like coverings of those subsets. So for the usual category of open subsets, these are just like open covers. But you could also say maybe I'm only looking at like relatively compact subsets that are open, and I only consider finite covers. This is a perfectly valid category, and this is a perfectly valid growth and topology. So you can restrict this thing. So you're unlucky enough to work with something that isn't compact. You can kind of have this pseudo fix that only really worries about finite collections of subsets instead of arbitrary collections. So you can start doing like problems from functional analysis using language of like sheaves and algebraic geometry, which is annoys analysts to no end, which I think is really funny.
Right. Yeah. I believe that I will need at least 2 years to
Oh, of course.
right to have a view of the scope that it could be right.
I met
There is so many connection that you can construct between things using this. It is like the meta language of all mathematics.
Yeah, I think an important takeaway from category theory is that there's no such thing as a distinction between pure and applied mathematics. All math is applied from someone else's perspective.
Right.
And yeah, I like it a lot. The first month that I started my grad school thing, which was a long time ago, my advisor gave me a book on category theory. He's like, I think you're gonna like this, and I have been reading it for about 10 years now, and I think I understand a good amount of it, but definitely not the entire thing.
What was it? Do you remember?
The book is called Sheaves on Manifolds.
Okay. Right.
Yeah, so it is a general way of, its goal is to be able to talk about problems from like linear differential equations, like PDEs on manifolds, to solve them using like algebraic topology techniques, which is kind of cool. So you can regard like differential equations as, it's sort of like if you think about a differential equation as determined by a differential operator. You can look at like algebras of operators, and this has algebraic structure. And you can look at all these other things.
I would say that when I took the first look at category theory, I don't understand why, but I didn't have my first look to category theory until the final year of my graduate right at the final step of my graduate path, and I don't know why. I will say that category theory maybe should be taught at the first or second course, maybe, or I don't know. It's like I feel that if you have a good teacher, you can understand it. And when I was looking at it, I was thinking that I remember that I was thinking I still think this way, that okay, so mathematics feels like it is about understanding that all is algebra. Something that you seems that it is not algebra. Indeed, it is. So it is like that's the reason why I like algebra so much. It's right, because I felt that mathematics is somehow about understanding that all, at the end of the day, all is algebra. Topology could be algebra, logic could be seen as algebra, analysis could be seen as algebra. So
Yeah.
because this category this language
Mhm.
is algebra.
Mhm.
I feel that it is a higher algebra.
Yeah.
Mm.
That's actually a whole field, higher algebra and higher category theory. Um, um, that looks like a bunch of, like occultist mystical works. I don't really understand it, but it seems important, and they keep getting funding, so it must be important.
Right, should be
Mhm.
right.
Like doing type theory or homotopy type theory as a foundation of math is kind of an really interesting thing. Like yeah, I think it's a really important thing. I was probably corrupted pretty early on in undergrad by these ideas. My group theory professor in undergrad took me aside once in his office hours, and he just like stared at me, and he's like, um, gave me. He's like, what the fuck did he even say? Basically, this kind of equivalence principle that isomorphic objects should be considered to be like the same objects.
Mm.
This is something called like the univalence property or principle in category theory. It's like if he's counting in French over there and I'm counting in English over here, are we doing the same thing or are we not doing the same thing?
Mm.
Yeah, I kind of like that show. My young impressionable mind, I was like, whoa, that's really deep, man.
Right.
Yeah.
Right.
Yeah, he said, like, what does it mean for two things to be the same?
Right. And actually, that's the point. And it is not trivial. It is not
Mhm.
trivial at all. What does it mean to be equal? To be the same thing?
Mhm.
That's very, uh, and it is related to what's geometry actually also.
Mhm.
Um. Okay. I will try to share some resources in
Yeah.
Discord. Maybe not I will resources related to this. I will post them to our course. I will
Mhm.
post it in the Discord channel, but
Mhm.
maybe some resources about homotopy type theory
Yeah.
I could share some resources, but maybe I could if not it is not adequate to share it by the Discord channel for this course.
Just
I will share
message
you.
me.
Right,
Yeah.
exactly. Actually, there is a book I feel that maybe you already know. It is a famous author called Bartosz Milowski.
Mhm.
He is talking about functional programming, and
Mhm.
functional programming is completely related to category theory. Actually,
Mhm.
many Haskell construction. Haskell is a functional program language. Many
Mhm.
Haskell constructions innovations for the language are just translated directly from category theory. So,
Mhm.
and the next thing you will explain, you say that it is
Limits
uh,
and co-limits. Yeah.
limits and co-limits. Uh,
Mhm.
um, I understood this stuff well, I think, more or
Mhm.
less, reading the book Category Theory for the Working Programmer and
Mhm. Mhm.
explaining how to construct uh, product types,
Mhm.
the product data types as limits. And
Oh, okay.
right,
Yeah.
right, and right, and it was the book has nice drawings also,
Mhm.
so it is uh, the visual aspect of the book is appealing. So
Mhm. Yeah, I'll have to check that out. I've known that category theory is pretty heavily linked with like Haskell and other languages of that kind of form, but it's never been enough that I never had enough of a reason to spend a whole time learning enough programming to make it useful, other than like you know. So
Right.
it's like this is cool, but like I have like an extra year to sit down and like become a proficient programmer to make this useful yet.
Right. I I don't know how I was guided to learn more about functional programming.
Mhm.
I took an introductory course as a graduate student, but
Mhm.
later on I was just attending to some meetup groups. They were talking about types, theorems, and programming languages. Um, it is related to to type system for constructing programming
Mhm.
languages. Um, Actually, it is the base of functional programming, and it is the foundational stuff stuff behind that is category theory actually.
Mhm.
So that's right.
Yeah.
There is a nice link between category theory and logic, and that
Yeah.
and type type systems.
Mhm.
Right.
I think one of the examples I want to talk about in the upcoming lectures is some more applications like logic and set theory and category theory. You know, quantifiers. You know, for all and there exists as are actually like can be viewed as adjoint pairs of functors on a
Right.
category, for example, which is hilarious.
Actually, it will be very good for me to learn about that because
Mhm.
I am working. I will be working in set theory and model theory for the next 6 months.
Oh, okay.
I will be interested about finding models for some constructions,
Mhm.
and I will try to look at it from the categorical perspective.
Yeah,
Right.
I mean, you should definitely, you know, look back and like meditate on the UNETA embedding because that's really all about, you know, being able to model any locally small category on like a like generalized collection of objects modeled on C. Like this, like the image of the in this functor category is really like generalized objects that are modeled after the category C.
Right. Right.
It's like but now these things live in a bigger category where all finite limits and colimits exists, even if they didn't maybe exist inside the category C. Like if I have functors from any category that's small C into the category of like abelian groups, then suddenly this is an abelian category regardless of whatever C was. So it's a way of modeling these kind of things in different contexts.
Right. I feel that there is some very interesting connection that could be made uh, uh, related to uh, you know what can be compute and what could be what is constructible and what is computable and right, because there is a category of computable things, and it could be right interesting to look at.
Yeah. I mean, like computable things are essentially, described by like, some like finite collection of propositions about the thing. You have, all your like logical operations and like compatibility with like projections and stuff like this. And this is just maybe a collection of propositions in some internal language of a category or a topos or something.
Right. Great. I am very happy to to meet you.
Yeah,
Right.
of course. But I should probably let you go at this point. I have to
Right.
run.
Okay.
See you next week.
See you next week. I will try to spend time working on that. I will try to I will move to Chile this week. I have a flight, but I expect that I will have at least a couple of days to working of this stuff, and I will write in Discord. So
Okay.
keep in touch. Thank you a lot. Thank you a lot.
Of course. Yeah. See you. Good luck with the move. Yeah.
All right. See you.
Bye.